Hi, welcome back to the crash course in Computational Hydrodynamics. This is lecture 2, and I'm Daniel Price. So last lecture, if you remember, we discussed basic equations of hydrodynamics, and these were in the form, we have d rho dt, which I'm going to write it in Eulerian form because it's just more helpful for where we're going. So d rho dt plus div rho v equals 0 is our conservation of mass. We have dv dt plus v dot grad v equals minus grad p on rho plus external accelerations, and we have our energy equation du dt plus v dot grad u equals minus p on rho div v plus heating and cooling terms. All right, so the main thing we're going to talk about this lecture is the nonlinear behavior of these equations. So last lecture, if you recall, we worked out the linear behavior, and essentially we found that if you take a small density perturbation, say a sinusoidal density perturbation, then it will just propagate unchanged as a linear wave. And if you remember, we derived a dispersion relation, w squared equals k squared cs squared, such that delta rho obeys an equation that goes something like cos k x plus or minus sound speed time. So it's just a translating sine or cosine function propagating in, well, time and space, but just translating with time. So this lecture we're going to talk about the nonlinear behavior. And really, when we're talking about nonlinear behavior, we're talking about the terms that we neglected in the first lecture. So the main term that's important here is this v dot grad v term. So these are the terms that would be second order. So this term was completely absent from our linear description. And it's this term, well, that's going to do the damage. So the simple way to think about this term is to use, again, our Lagrangian derivative. So if you remember that our definition of the Lagrangian derivative, we had a ddt, which is defined as partial ddt plus a v dot grad. So that's an operator. So for example, that operator operating on the velocity would be the velocity dt plus v dot grad velocity. All right, so we're going to use this big ddt because we understood that last lecture, what the meaning of that time derivative is. And if you recall, it's the meaning of the derivative for something that's sitting, moving with the fluid. So that's why we call it a co-moving derivative. So it's the co-moving derivative or time derivative. So this is going to give us the insight into the nonlinear behavior because we can understand what this v dot grad v term does by thinking about what happens in a Lagrangian sense when you're moving with the fluid. So we're going to pay attention to the momentum equation in particular. So let's just rub out a couple of things. So we're not going to worry too much about the energy equation. We're going to think about the nonlinear behavior of the momentum equation. Okay, so let's do that. And it's very helpful to think of the sort of extreme cases. So whenever you're studying partial differential equations, it's helpful to consider what each of your terms does. So the simplest thing to do would be to imagine there's a fluid with no pressure, right? So the right-hand side is just 0. Now this is just a fluid consisting of dust or other pressureless material. So we're going to worry about the nonlinear behavior of our equations of fluid dynamics. Sorry, that was a terrible line. And we're going to consider the following. So let's just write some things down. So the main term missing from the linear analysis is the v dot grad v term. So that's a fully nonlinear term because it would be a delta v dot grad delta v. So let's consider the following equation And this is called Berger's equation. Named after burgers. Nothing to do with hamburgers. And it's equivalent to the following. It's equivalent to simply saying dv dt is 0 in the co-moving time derivative. So if we consider the behaviour of Berger's equation, we can understand what happens. So for example, consider the curves given by dx dt equals v in the x time plane. So you've seen one of these diagrams before. If you recall, last lecture we drew a diagram about the characteristic solutions for our waves. And I mentioned that this, so this was time, and this is x, and this is x plus sound speed time, and this is x minus sound speed time. But let's consider what happens to this equation now. We've got dx dt equals v and dv dt is 0. So we're just moving at a constant velocity. What happens? So let's, for example, let's consider a 1D wave. So let's imagine that velocity, let's imagine a velocity in the x direction. So we just have a velocity x, which is a function of x, equals to something, some amplitude sine of kx. So that's in space. We just got something like velocity with x, and we've got just a simple sine function. All right, so let's now think about what happens to this wave. So we need to make a space in this kind of x time plane. Let's think about what happens to each blob in this wave. So hopefully some of this is revision if you've taken our third year fluids course. But the only thing we have to consider is this co-moving time derivative of velocity equals 0. So that means we just need to think about, if you're sitting on any part of this wave, how you will change with time. All right, so let me make a bit of space and we'll do this. Keeps you fit, this whiteboard stuff. All right, so we're going to think about, what happens if you're sitting on this wave. So we have the following. So this is just what I drew down below. Velocity is a function of x and some sine function. And let's consider 3 different places sitting on this wave. So A, B, and C. Okay. Now for each of these equations, so we recall that each of these has dv dt equals 0. So they each have a different velocity, but they all keep their initial velocity. So blob A will simply move to the right. Blob B will stay exactly where it is, and blob C will move to the left. But each of them will keep their initial velocity. So C has a negative velocity, A has a positive velocity, and B has 0 velocity, so it stays at rest. All right, so let's just write that down. Consider, fluid elements, A, B, and C. Each retains their initial velocity. So basically A is moving with a positive velocity. So this is just recapping what we just said. B is not moving. And C is moving with a negative velocity, minus v. Okay, so sometime later, so finite time, And what you're going to see a little bit later is what we care about is actually the velocity relative to the sound speed. So the importance of these nonlinear effects, we've accentuated in this case because we've said the sound speed is 0. We've taken the 0 pressure on the right-hand side. So the velocity is always important relative to the sound speed in our case. So at some later time, so A would have moved slightly to the right, B would not have moved, and C has moved slightly to the left. So our wavefront becomes distorted. Hopefully you can see that. And later still, we would have the following. So you can imagine this keeps moving. So this wave would keep what you call steepening. And later still, so there's velocity and x, velocity and x. So B is still exactly where it was before. A could have moved all the way over here, and C could have moved all the way over here. So, so instead of, so our wave would steepen, but then the actual wavefronts would actually cross. So that would mean our velocity field could have double-valued solutions here. So, so in words, so this phenomenon is known as steepening, and it's basically the nonlinear behavior of waves. So one part of the wave, so different parts of the wave now move at different speeds. And this is very different to the linear case when the entire wave just translates along. So, so the solution steepens. And, well, what happens down the bottom here, so it eventually becomes double valued. Which, for a fluid, is unphysical. So there's other kinds of systems. So, for example, a collection of dust particles which don't feel each other, they would simply pass through each other exactly like that and give you a double-valued velocity field. Same with dark matter. But let's think about this in the xt plane. So I have the following again. So this is time, and this is x. So this is blob B, this is blob A, and this is blob C. So A is moving with a positive velocity, so this is moving with a positive velocity. B is not moving at all, so it just translates forward in time. And C is moving to the left. And so these are exactly the same thing as what we found for the linear wave solution. So these are what you call, so this is a line as x equals, minus vt. This is x equals vt. And so these are the characteristics. So these are the characteristics, characteristic curves for Berger's equation. And in our simple example, so what we have is that velocity is constant along characteristics. So another way of putting that would be that the characteristics of Berger's equation are the lines v equals constant. And we'll see, you've already got a bit of a clue that for the case of the full fluid equations, the solutions are going to be v plus sound speed or v minus the sound speed. All right, so just a technical definition as well. So these quantities so velocity being constant along a characteristic, if you're constant along a characteristic, that's called being a Reman invariant. All right, so let's just write that down. So quantities that are constant along characteristics are called Reman invariants. All right, and so this place where our characteristics cross, so here we say the characteristics cross. And this point corresponds to formation of a shock wave. So, where characteristics cross is what we call the formation of a shock front or shock wave. Now, that's because in a real fluid, the fluid is not allowed to become double valued. And so instead of this steepening behavior, so instead of the wave simply steepening and then becoming double valued, something has to happen here to make this simply become a front. Now, we've got a problem, and we're going to see this in a few minutes, that when our solution becomes a sharp front like this, our derivatives no longer exist. So for example, the gradient of pressure is infinite. The gradient of density is infinite. So actually something goes wrong with the fact that we've written down our equations as differential equations because our derivatives no longer exist. And just a final aside, so this, what we've just done by doing our simple dv dt is 0, that's an example of using what's called the method of characteristics. So above is a simple example of using the method of characteristics I'm going to run off the screen here, of characteristics to solve a PDE. And for hyperbolic partial differential equations, which is basically equations that look like the wave equation, and if you think this was new, for example, this was done by, for example, Reman in 1859, or a book by, famous book by Courant and Friedrichs in 1948. And this method of characteristics is often used in numerical methods for helping to solve these equations numerically as well. All right, but we've got a problem, which is we're going to form these now discontinuous fronts. And so we've got a problem with our equations of hydrodynamics. So we're going to have to rewrite them in a way that can cope with the fact that you have these discontinuous jumps in the fluid. And something remarkable is going to happen as well, which is there's something really special about the equations of fluid dynamics, which is that they contain, in the way that I've written them as the Euler equations, so we haven't used any physical viscosity. There is no dissipation in these equations right now. So I've written purely differential equations. I haven't written any irreversible dissipation terms. All the equations conserve energy. They're adiabatic. That means there's, in principle, nothing that tells me, nothing that should be irreversible in my set of equations. But you can maybe guess already that forming these shock fronts, something irreversible happens. And that's because, you know, you're losing information. So essentially, you can imagine that if you are going double value, you can imagine reversing that and getting back what you had. But when you form a shock front like this, you can imagine you're basically losing information at the front. And losing information in physics is called increasing your entropy. So something's going to happen which is interesting in terms of thermodynamics here. And you're going to see that at the end of, once we've finished our derivations. So the procedure is that we need to do something to our equations of hydrodynamics. We need to do something that allows us to cope with the fact that there's a discontinuous derivative. Also, the derivatives will go infinite. But if you remember, we can simply go back a few steps and remember why the kind of bigger picture here. So if you remember from lecture 1, the bigger picture was that our equations are supposed to be expressing physical principles. So those physical principles are more general than just a set of differential equations. So when we're thinking about what happens across the shock front, we can go back to our original principles. If you remember what they are, that's conservation of mass, conservation of momentum, and conservation of energy. So the first step is to rewrite our equations in what's called conservation form. So conservation form, well, here's my definition. It's astronomer's definition, sorry. You got a partial time derivative of a thing plus the divergence of the flux of a thing, where thing is some scalar or vector field, and that equals 0. So physically, basically this says the amount of material per unit volume is only changed by a flux of material into or out of that volume. So for example, the continuity equation, remember that expresses our conservation of mass. We've already got that in a conservative form. It says d rho dt, which is the mass per unit volume, and the divergence of rho times v, which is the flux of mass into or out of that volume, equals 0. So we already have this, but the problem is this part, right? So we've got spatial gradients of something which, so we're going to have infinite spatial gradients here. So we need to deal with this term. So the best way to deal with that term is now to simply integrate this over the volume. So if we integrate over volume, we have, so we get a d dt. Now the integral can go into the time derivative because those two commute. Integral of rho dv. Now you'll notice that's simply the mass. So that's simply the total mass in a volume. Now this one is the integral of divergence of rho velocity dv over the volume equals 0. Now you've seen equations like this before, so we can simply use Gauss's theorem to turn our integral of divergence into a flux through a surface. So we have the d dt of the mass through our volume. So time derivative of the mass is now simply equal, I'm going to put it on the right hand side, the minus rho times the velocity dot the surface integral. So this expresses physically what we were trying to express, which is that basically the mass only changes because, or mass in a volume, because of mass flow through the surface, so in or out of the surface. So if the velocity is 0, there's no flow through the surface, then the mass in the volume doesn't change. This is obvious. But what we've done by a bit of magic now is we've written our equations in a form which is called the integral form, where discontinuous solutions are allowed. So we can think about mass flux without thinking about differential equations. So we've gone to something more general here. And this is what allows us to treat these discontinuous solutions that inevitably come in our equations of hydrodynamics. So the same procedure is true for the momentum and energy equations. So I'm just going to write them down for you, and putting these into conservation form is an exercise on the problem sheet. So you guys should be able to have a crack at this and come back when you need help. So the same applies to the momentum equation. So what we had before was dv dt plus v dot grad v equals minus grad p on rho. And this equation becomes, in conservation form, we get a d dt Now I'm going to write it in using tensor notation. So just Cartesian tensor notation is very helpful. So instead of writing v, I'm going to write a vi. So the index is just the vector index, so 1, 2, and 3, or x, y, and z. And because it gets a bit messy, so we simply get, well, so it's the divergence. Well, actually, you can write this in what's called dyadic notation. Maybe let's do that just to begin with. So ddt of rho v, so that's the momentum per unit volume, and plus the divergence of, well, it's basically pressure times the identity matrix, plus density times velocity times the velocity. Now, this is not a dot product, this is a rank 2 quantity. That's why it's kind of easy to use tensors. But that's the momentum equation in conservation form. Or if you're going to write this in tensor notation, we could simply write that as rho vi plus, this is a ddxj. This is a p delta ij. So delta ij is the Kronecker delta. So that's just a dp dxi effectively, which just is a pressure gradient. And this one is a rho vi vj equals 0. So those are the same, those are equivalent expressions, just different notation. And I find once you start to use these rank 2 quantities that I much prefer to use tensors just because things become much more clear. This is unambiguous. So remember, in Cartesian tensor notation, so a repeated index implies a summation. So this is many terms here. So this is a rho vx vx, rho vx vy, rho vy vy, rho vz vz, rho vz vx, rho v. So there's a lot of terms here, and this implies a summation over the j index. So that's a x plus y plus j. That's x plus y plus z. All right, and finally the energy equation. So the energy equation. Now, so the notation I really hate, just for discussion, I really hate this kind of disgusting outer product notation, but sometimes you'll see this. I really find this completely ugly, and you should never use it in my class. But so for the energy equation, we define the energy per unit mass is the half v squared plus u. So that's the total energy per unit mass, because remember, it's not the thermal energy that's going to be conserved in this volume. It's going to be the total, it's the total energy per unit volume. And so we end up with the following. So we get up with a ddt of rho e, that's the energy per unit volume, plus the divergence of, now it's rho e plus p, v equals 0. So that's the same thing in conservation form. And so again, it's quite easy to transform these both to integral form. So let's get there. So if we take our two, this is a momentum equation, and this is our energy equation. So in integral form, we have the following. So we have ddt of the integral of rho v dv. So that's a vector quantity. It's the total momentum in the volume. And that equals the surface integral over pi plus rho vv. That's dot with the surface integral. So again, you have to be careful about the rank here. This is a rank 2 quantity. So one of these ranks belongs with the left-hand side, and one of these ranks is dotted with the ds. So again, if it gets confusing, just switch to Cartesian tensor notation. And the energy equation is the same thing. So this is just a rho e over the volume equals, this should be a minus. This gives us a minus, the surface integral of rho E plus P V dot ds. All right, so we've got our three equations now in this conservation form where we can deal with discontinuous solutions. So essentially we don't need to consider any more, so the fluid quantities don't need to be differentiable. So the fluid quantities TTs no longer need to be differentiable to find solutions. Okay, so we're going to jump into the actual shock solutions based on these equations in just a second.